Bismillahir Rahmanir Rahim. Assalamu alaikum. Welcome to the fourth lecture of Fundamentals of Electrical Engineering. Uh, I am your course instructor Muhammad Hassanul Haq. Today we are going to talk about, this is lecture number 4. Today we are going to talk about the basics of electrical circuits, current, voltage, power and energy concepts. In the last week, I've also given you an assignment related to a documentary that was titled uh, Shocken of the Story of Electricity. And I hope that you have started watching that documentary. So, today we are going to talk about these four concepts and we are going to do some numericals as well. Let's start today's topics by first let me show you there is something called the voltage and current sign convention. So when you're talking about DC circuits, there is a sign convention that is followed. Now, let me write that down. Voltage and current sign convention. What does this mean? Sign convention means that you are going to put a certain polarity of across every voltage source and a certain direction of current through every element or current source. So what are going to be the voltage and currents, how they are going to be how they are going to be given polarities, and how the currents are given different signs. Let me show you that. So for example, if you have a battery like this, and this is the positive terminal of the battery, this is the negative terminal of the battery. Let me call the positive terminal A, the negative terminal B. Then we can say that VAB is equal to whatever the voltage of the battery is. For example, this is a 9-volt battery, so we can say that VAB is 9 volts. We can also put this in a slightly different way. We can say that VBA, if you were to measure this battery using a voltmeter such that the positive terminal was here and the negative terminal was here, what would happen? If you measured the battery voltage in the reverse polarity, then you would get minus 9 volts. This is the voltage sign convention. This is how we are going to assign signs to voltages. So if there is some two terminals across which there is some voltage, and there is the amount of voltage, you can refer to those two terminals in this way: V voltage measured from A to B, and then give the voltage that's present there. If you reverse that BA, then a negative sign is going to appear with the voltage. Similarly, there is a current direction convention. Convention means simply a rule that has been agreed upon by everyone in order to ease or simplify the process. So we are just simplifying the process. Let's say this is a resistor, and let's say this terminal is called A, and this is the B terminal of the resistor, and some current I, let's say it's 5 amperes, is flowing through that resistor in this way. You can see that the current is entering the A side and leaving the B side. Its arrow is pointing towards B, so it's going to leave from the B terminal. We can describe this current as IAB and say that its value is 5 ampere. Conversely, we can say that IBA, if you were to think that the current was flowing in the opposite direction, then there is going to be a minus sign associated with it. This is how voltages and currents are assigned different signs. This is a small concept that I wanted to discuss with you before moving ahead. Now let's move to the next idea for today, and now we are going to do some interesting things. And the concept that we are discussing now is power and energy. So our topic is power and energy. And mind you, we are talking about electrical power and electrical energy. So we start with energy, and you know that energy is the capacity to do work. So energy is simply the capacity to do work. And when we say work in our course, it means electrical work. So it can be running a motor or lighting up an incandescent lamp. This is energy. What is power? Power is simply the capacity to do work per unit time. So power is simply this whole thing divided by time. So I can say power is capacity to do work per unit time. And let me put it in a slightly different way. Let me give it a mathematical definition. So the mathematical definition, you know that for, I would start with power. So power is simply dW, the work done per unit time. Previously, we saw the definitions of voltages and currents. We can relate to them as like this. Work done per unit charge was voltage. You remember that? And the rate of flow of charge with respect to time was, you remember that it was current. So you can see that these two terms are going to cancel out, dq here and dq over here. And when those cancel out, you are going to end up with dw over dt. So this multiplication simply gives you the power. And what are these two things? This one here is the voltage, this one here is the current, hence power is voltage times current. That's the definition of electric power. Uh, as far as the units are concerned, you also already know the units. The units for power in SI system are watts, that's already decided. And the unit for electrical work or energy is joules. So this is how voltage and power and energy is defined. Let me give you a perspective what the two things mean. For example, let's see, let's have an example that we have some voltage flowing in a circuit. This is voltage with respect to time, and let me just make it like that. It's not sinusoidal, it's just going up and down. And then at the same time, due to that voltage, there is a certain current flowing in the circuit. So for example, this was the current I. Now these two need to be multiplied one sample at a time in order to get power. So power is going to be the multiplication of these two numbers or these two graphs. And let's say if the power value, if you multiply voltage and current, it looks like this. So this is the power coming from some voltage across a battery or any element, and some current flowing through that element. And this is the amount of power. This is the graph for the power. Now let me clarify. Power is defined at every instant. It's going to be different at every instant, unless voltage and current are constant. If both voltages and currents are constant, then the power is also constant. However, if they are changing like here, you can see, then the power is also going to be changing at every instant of time. If I ask you what is energy here, then remember that energy in this scenario is not any single value. It's not this value or it's not this value. Energy is going to be defined for a certain time period. For example, from the starting time to this timestamp. And you're going to integrate this whole graph and find the area under the curve between the two timestamps. And this point is going to give you, this integration is going to give you energy. This is also true from this definition, P equals dW over dt. How? You can see that you can keep W on one side, dW on one side, P dt, and then integrating both sides, you are going to get W equals integral P dt. So remember that energy is the sum up of all the values of power for a given duration. You have a single number that comes out from the whole graph, from one timestamp to the final timestamp. On the other hand, power has a value that's changing at every instant of time. So sometimes I say that uh, energy is simply power frozen in time. This is just a neat way of remembering this simple relationship. Now, when we talk about power, there is a very important concept in electrical circuits. You remember, you have just seen that there is a concept of voltage and current sign convention here. If there is a sign convention for voltage and current, it means that there is necessarily going to be a sign convention for power. So let me bring that topic here. So sign convention of power, or I can say, let me write it like this, sign convention of power. What is that? In your textbook, this topic is titled passive sign convention. So don't bother about that. We are not going to try to understand why passive sign convention is used, why this terminology is used. Just understand that this means passive sign convention actually means sign convention of power. What is the sign convention of power? So let me state that very quickly, that, and I'm going to put it in quotation marks, if current enters the positive terminal of an element, positive terminal of an element, and any element, it could be a resistor, it can be a battery, then we take power as positive and power is consumed. Then P is positive and considered to be consumed. Consumed means dissipated. The energy is actually destroyed by that element. It has eaten up all of its work capacity. However, if the current is not entering, or if the current is leaving, or I can say that if the current is entering the negative terminal, of an element, then we say that the power is negative and considered to be generated. So by the word generated, we mean that the power is being provided by that element. It can be a battery or it can be a solar panel. something like that, that can generate power. So this sign convention in simplest terms means that P is positive when current enters the positive terminal of any element, and P is negative when current enters the negative terminal of any element. Positive power simply means the power is being consumed by that element, and negative power means that that element is actually a source of energy. So, for example, if you have this battery over here, this element, we don't know the element over here. So, for example, this there is an element with 5 volts across it like this, and you have a circuit, and you can see that the current is entering like that. 2 ampere is entering like that. Then the power value is 5 twos 10 watts, and since the current is entering the positive terminal, it's going to be positive power. And we can easily say that if we observe positive power, that this element is consuming power. It's not a battery, it's not any kind of voltage generator or voltage source. It's actually some kind of a resistor or a light bulb that can consume power. On the other hand, another example, if this element has this voltage across it, and you observe in a circuit that the current is 2 ampere in that direction, so you can see that the current is leaving the positive terminal, or you can extend the idea yourself and see that it means that the current actually entered the negative terminal, and when the current enters the negative terminal, power is negative, which means this element could be a battery. One important and you can say it's a side note that the law of conservation of energy dictates that the power in a circuit is also conserved. This is also very important to understand. So conservation of power means that in any circuit, the sum of all the powers of all the elements, I means element number, I denotes the element number. So for example, in a circuit there are 1 to n elements, there are 5 resistors, 2 voltage sources and other things, and they are all consuming or generating power. The law of conservation of power suggests that all the sum of those powers is going to be 0. And this is a very useful relationship. Sometimes we solve circuits using this relationship. So we have quickly talked about voltage. We have quickly talked about power today. First, we talked about voltage and current sign convention. Then we talked about power and energy. And now we were talking about sign convention of power and conservation of power. We have seen quite many equations by now, and I think it's right time to start applying those using numericals. And I must tell you that in this course there are several numericals, and we need to solve them um, many times using manual methods, many times using calculators, and that's why I would start doing numericals right from today. And in each lecture, we are going to solve some numericals so that your understanding of the concept gets better. So here is the first one about what we have learned. So there is here is a circuit. You can I hope you can see it properly. The circuit has this voltage source here. This is plus minus a voltage source 2 volts with 8 amperes, and this is an element. We don't know the kind the type of element with 5 volts, and we don't know the current. We actually know the current. We are going to see that in a moment. And this is another voltage source. You can see plus minus means voltage source. This is a different kind of voltage source. I'm going to talk about it in the next lecture. This is called a dependent voltage source. We are going to talk about that. And you see it's generating 0.6 times I volts. And this italic I, you can see, is already given to you. It's I equals 5 ampere over here. And similarly, this final element has 3 volts across it, and 5 volts are entering. Now, if I ask you to calculate the power absorbed by each of the elements, if I ask you to do that, how can you do that? It's quite simple. You are going to use the equation of power. So you need two things. You need to know that P equals V times I. That's one thing. And you also need to know that P is positive when I enters positive terminal. And similarly, you also need to know that the converse of this is P is negative when I enters the negative terminal of an element. You need these three facts to solve this question. Let's solve this question now. So for this element over here, you can see that uh, this branch has this current flowing, which is 8 amperes. You can see that the current is going up and then going right. So some current enters the negative terminal. If that 8 ampere going up is shown over there, it means it must have come from here. So 8 amperes must have come from here, from the bottom, which means the current is entering uh, into the negative terminal. So the power P1 is given over here. P1 is minus times, because the current is entering on the negative terminal, and the power formula 5 volts times 8 amperes. 5 times 8 is minus 40 watts, which means that even though it's not shown over here, uh, it means that this element is not a resistor. It's not consuming power. It's not a light bulb. It's actually some kind of voltage generation source. It's generating some power over here. The negative sign tells us that. Even though the block is not representing anything, this square block does not mean it's a resistor. A square block element means it can be anything. Let's find out the power P2 over here, and you can see it's the power of this voltage source. So P2 is going to be, the 8 ampere is entering the positive terminal, so it's going to be positive. So simply positive 2 times 8, and that is 16 watt. Interestingly, positive power means that the power is being consumed. So if this is a voltage source or a battery and power is being consumed into it, it means that battery is being charged. It's not actually delivering power, it's actually storing power. It's being charged. That's why it's consuming power. Positive. Let's compute P3. P3 is simply voltage times current. So what is the voltage P3? This is a slightly confusing example. So P3 voltage is simply this expression which is written in front of the voltage source. So 0.6 times I. So 0.6 times I is the voltage, and then multiplied by the current. The current is 3 ampere. And according to the passive sign convention, the power convention, we need to understand that the 3 ampere is entering the plus terminal, which means positive sign. And this is going to give you the power consumed by this device or generated by this device. And you can see I is over here. We need to find I in the circuit, and that I is 5 amperes. So let me put that 0.6 times 5 times 3. and that results in, let me write it over here, 15 times 6 over 10. 0.6 is 6 over 10. You can use your calculators here. I'm just going to solve it like this, and this is going to result in 15 times 6 is going to give me 30, 90 over 10, or simply 9 watts. So P3 is 9 watts, and since it's positive, it's actually consuming power. So if this were a voltage source, then this voltage source was not delivering power, it was getting charged. Let's compute the final power here, P4, and that power is, you can see, uh, voltage is 3 volts times current is 5 amperes, and the current is entering the positive terminal, so it's going to be positive power, and it results in 15 watts power consumed. So this could be some kind of a bulb or a resistor which is actually consuming the energy. So this is how you can find out the powers applying this formula and the passive sign convention. You always need to use the passive sign convention when you are finding out powers. Remember that. And uh, you can do an interesting observation over here, that so if this circuit is a real circuit, a real world circuit, and it's working, then even though I haven't asked you to apply the conservation of power, but if this circuit were a real world circuit, then conservation of power should also hold for this circuit, and sum of all the powers should give you 0. So let's quickly see if that's true. So you can see that the P1 plus P2 plus P3 plus P4, let's check what's the sum. So P1 is minus 40, P2 is 16, P3 is 9, and P4 is 15. And you can see that 16 plus 9 is 25, and 25 plus 15 is 40. So what you get is this, and these two cancel, and the sum of all the powers in the circuit is 0. If this circuit is a real world circuit, you can see, you can understand that if I would take some arbitrary value over here, instead of 8 amperes, if I would have taken 7 amperes, then this might not have been true. But if this circuit was a real circuit, then sum of all powers must be 0. That's the law of conservation of power. This is how we are going to compute power, and this is how we are going to use the law of conservation of power. Now, let me discuss some other examples also very quickly. So, these are two examples, and in these two examples, you are being asked to find, in the first one, you are being asked to find, you are given this graph, which is the charge flowing in a circuit. Remember, note that this is charge, or Q with respect to time. X-axis is time, and you are being asked to find out the current. For this, you need to remember the definition of current, that current is the rate of flow of charges. If you want to find that, I'm just going to help you in framing this question, the actual solution, you should be doing that. The solution is present in the handout. You can look at the handout there, but I'm just going to give you the hint how you are going to solve that. So the first thing you need to do is you need to define q of t, the function. And that function, you can see that it needs to be defined for the three different time spans. This one, and this one. So this is a piecewise function. The first part of the function would be defined for time which is greater than equal to 0 but less than 2 seconds. The second part of this is going to be between 2 seconds and 6 seconds, and the third part is going to be between 6 seconds and 8 seconds. This is how you are going to describe the function in three parts. This is what you need to do in order to find the derivative, because you need to find the derivative of q in order to find I. And to find the derivative, you need q itself. The graph is going to help you in doing that. And you can see that this first part, this first line is simply y equals mx plus b. You can use that representation, and you can see the y-intercept is 0. So this first line is simply going to be y equals m. Let me find the m over here. M, the slope over here in this side is y2 minus y1, which is 50 minus 0, over x2 minus x1, which is 2 minus 0, and results in 25. So the slope is 25 and the y-intercept is 0. I can say that q of t for this time span is simply y equals mx, and m over here is 25. X-axis over here is the time axis. The second part, which is this, let me use another color. The second part, which is this slope down, you can easily verify that the slope of the second part is the same as the slope of the first part. So the second part has a slope which is negative since it's going down, but the numerical value of this slope is the same. So it's minus 25. And what is the y-intercept? So if you can you can do it graphically here. If you can just simply extend this line over there and see where the y-intercept is going to hit, you would be able to find that the y-intercept is actually at 100. So the b value here is 100. Using this slope m and this slope b, I can say that the second part of the equation is minus, I'm sorry, the second part is over here. So the second part, which is over here, is minus 25t plus 100. This is the second slope. And the third part that you need to solve, which is over here, this one in the blue, is again you can see the slope is same as the first two parts, and I'm going to say that the slope is positive and same as before. So m is 25, and this is straight line has a y-intercept, you can see, which is, I think, going negative. Of course you can verify how this is going to work. I'm just going to give you the slope directly. So it's I'm just going to give you the y-intercept over here directly. You can verify that yourself. This is minus 50, minus 100, which is going to be minus 200. And you can put those in form of an equation, and the q of t between 6 and 8 seconds is going to be 25t minus 200. So this is q of t. Now you can apply dq over dt over each and every one of these equations, and the current I of t is going to be described in the same way. It would be between 0 and 2 seconds first, then it would be between 2 and 6 seconds, and finally between 6 and 8 seconds, and your answer is going to come up over here. This is an example from your textbook. So this is example 1.7. This is problem 1.7. You can verify that from your textbook also, whether you have got the right answer or not. Finally, I would ask you to sketch this. The question asks you to sketch. So let me just quickly give you a quick hint that the current sketch is simply going to look something like this. Something like this. So this is going to be how it's going to be. I'm not telling you what are these values. You need to do it yourself, but the current sketch is going to look something like this. Some horizontal lines and then going down and then coming up. Similarly, let's solve this second example over here quickly, which is 1.8. In this example, what you are provided is current, the graph of current I, and it's note that it's in milliamps, and you are also provided time in milliseconds. X-axis is time in milliseconds, and you are being asked to calculate the total charge through the point. And what is charge? You know that we have to use the same equation over here again. So dq over dt. Q is the charge. If you want to find out charge, you can rewrite this equation as dq equals I dt, and then integrating both sides between the range of t0 to t1. t0 is the 0th time and t1 is the current time, and what you get is on the left hand side you get q between t0 to t1, and on the right hand side you get simply the integral t0 to t1 I dt, and this is simply integrating the whole thing. Now you must be careful on the left hand side in these kind of integrations, because on the left hand side, if you want to expand that, let me do that over here. You are going to get q at time t1 minus q at time t0 is equal to integral t0 to t1 I dt. This is the actual equation, and to solve this you need to have the value of I. I needs to go into this equation, and then you can do this integration. This example can be solved in two ways. One is that you use this equation and apply it over here, but note that this equation also needs to be split into two parts, this first slope part and then this horizontal line part. So it's going to be a piecewise function. You would need to write I of t as a piecewise function and then use these formula. There is another way of solving this, and that way is simply, since you know that uh, integration is simply area under the curve, and since this area seems to be very simple and easy, you can simply find the area under the curve here and the area under the curve over here, and add those two area to give you the value of q. You would not need to integrate, you just need to use your um, geometrical formula to find the area under the curve. That is also possible. So you can see that this triangle is going to be solved in this way, that it's going to be half of the base times the altitude. So the base over here is 1 millisecond. You need to use millisecond over here, otherwise you are going to get in trouble if you don't use the milli subscript over here. If you're just going to use 1, then you are going to get in trouble, because remember that the charge is in coulombs. If you want to get coulombs in the final unit, then you would need to keep the units in SI form. So the current should be taken in milliamperes and the time should be taken in milliseconds. Only then the final unit of charge would be coulombs. Otherwise, it would be some milli version, and then that would be wrong. So the base is 1 millisecond, and the altitude over here is 10 milliamps, and the area you can find. Similarly, you can find the other area of the rectangle. So breadth into height, the breadth is 1 millisecond and the height is 10 milliamperes, and you multiply that and sum the two together, the final number would be in coulombs. That is the second way of solving this problem. So these are some methodologies of solving problems. Let me just quickly finally come to the final example over here, and then I'm going to give you um, a home exercise. So the final example over here is this circuit, and you are being asked to find V naught. Now, I haven't actually discussed with you any techniques of solving circuits as far as today. In this lecture, we haven't seen any specific circuit solving techniques. However, you know that power can be calculated easily using P equals VI, and you also know that the sign convention of the power, you can easily apply that to an equation of power. Using those two things and combining them, the first thing is power. You know that power is VI, and then there is this sign convention of power. You know about that. And the third thing that you know by today is that sum of all powers in a circuit needs to be 0 if that circuit is conserving energy. So using these three things, we can solve this circuit easily. What you need to do is start writing power for P1. This is, let's say, P2. This is P3, P4, P5, P6. Write the correct equation of power for all these: P1 plus P2 plus P3 plus P4 plus P5 plus P6, and that should be equal to 0. And you can see in the whole circuit that only V naught is the variable that's not given to you. I naught over here, which seems to be not given, is actually provided over here, 2 amperes. So when you write this equation and you equate to 0, you are going to get the value of V naught, and that would be your answer. One last example for this course. I'm going to share the answers in the handout. So if you want to look at the answers, you need to go and read the handout. Finally, this equation. Now this is an interesting graph. I'm just going to explain this graph, and we are going to solve it inshallah in the next lecture. So this graph says that you can see the x-axis is in hours, and these are 12 hours, and this is the consumption of an energy of a house. So this is the power value. So at 12 in the midnight, about 200 watts of power is consumed all over here. Then somewhere around 6 a.m. in the morning, the power goes all the way to 800 watts and then comes back again, and then 200 watts are being consumed, and finally goes back to 1200 watts in the evening at 6 p.m. and then comes back and then goes to 12 a.m. in the 12 a.m. to 12 a.m. midnight. So this is the consumption of electricity over one whole day between 12 a.m. and 12 a.m. the next day. So these are 24 hours. These are 24 hours, and this graph tells you how a house is consuming electricity. Now, before we go ahead and solve this problem, we are going to do that in the next lecture. Let me discuss quickly that energy is usually represented in joules. The unit of energy is considered to be joules. In our energy consumption of household electricity, when we talk about household energy or electricity consumption, joules becomes a very difficult unit to handle. And the better unit of energy, there is another unit of energy, is kilowatt hours. Kilowatt, you know, that is power, and hour is, you know, is time. And you remember from the formula that power is dW, the energy per unit, dt, the time. You can easily see from here that dW is P times dt, or power times the time. But in this formula, we assume that every quantity has SI units, so power is in watts and dt is in seconds, and watt seconds becomes joules. If you replace power in and use kilowatts as your unit for power, and instead of using seconds you start using hours as your unit for time, then the energy consumed would be in the units kilowatt hours. This is another unit of electrical energy consumption. We are going to talk about this and solve this numerical in the next lecture. So I hope you have started grasping concepts of voltage, current, power, and energy. And this is a very interesting example. We are going to solve this example next time. Please look into the handout, and there are other questions solved in the handout as well. So start understanding those questions. I'm also going to give you some practice sheets to do your own practice and have a grasp into these concepts. We are not going to solve very difficult problems here. In this course, we are going to solve very interesting and thought-provoking problems that are going to give you an understanding of the electrical systems that are around you. For example, this is a good graph representing the energy consumption in a common household. And we are going to see how much energy is consumed in this house in a day. By the way, you must know that your K Electric or energy company, whatever energy company that's providing energy to your house, charges you according to how many kilowatt hours you have consumed. Your billing unit of electricity is in kilowatt hours. So this unit is much more useful than other units. So with this, inshallah, I'm wrapping up for today with this. I hope you have understood these concepts. Inshallah, we are going to meet in the next lecture and discuss more about energy.